What I do on a day-to-day basis is create vulnerability signatures to detect vulnerabilities on operating systems, third-party applications, and stuff like that. A few months back, I was working on a interesting Apache Reverse Proxy vulnerability, and I was trying to create a signature for that particular issue. And what happened was that once I created the signature, I was just curious to look at the patch to see what was happening, how they patched the issue. And while reviewing the patch, I figured out a way to bypass that patch and ended up discovering a variant of the vulnerability. So in this talk, I'm going to walk you through the entire process of how I wrote the signature, discovered the, looked at the patch, and then discovered the new variant of the vulnerability. So let's get started. What should you expect from the talk? We are going to be doing 4 things today. First, we are going to take a look at an older Apache Reverse Proxy issue. Then we are going to be looking at the patch to see how that issue was patched. 3, we are going to create a proof of concept on the fly to see how learn how to create new exploits. And then finally, once you've created the exploit, we are going to try and exploit the issue. Okay, so since we are on a mission of finding a vulnerability in Apache's reverse proxy configuration, first let's understand what proxies and reverse proxies are. I'm sure all of us have used proxies to access the internet. What we basically do is configure the proxy through our browser. So what is happening is all your HTTP requests are passing through the proxy. And how the entire thing works is that a client makes a request, the proxy intercepts that request, the proxy would forward the request to the server, it would get a response back from the server and give it back to the client. So a regular proxy is acting on behalf of the client. A reverse proxy, on the other hand, it acts on behalf of the server. The basic steps are still the same. You make a request, the proxy would get the request from the client, it would pass it on to the server, and then whatever response it gets back from the server, it passes it back to the client. But what we're trying to get here is that a proxy is basically acting on behalf of the client, while a reverse proxy is acting on behalf of the server. So in case of a reverse proxy, the client has absolutely no idea that the pages that are being rendered are from a reverse proxy. To the client, it's just like any other web server rendering the content back. So let's see how this works in a typical scenario. So here we have a company A. Actually, just a second. Let me get the clicker on. Okay, so here we have a company A. It has a public IP address and a public domain at www.qualys.com. It has a registered DNS entry. So whenever someone is trying to access this particular URL, they're trying to access it from the internet. So it's publicly accessible from the internet. Now, I think this is not working. All right. So we also have a couple of application servers owned by company A. Both of these application servers are behind the firewall and within the DMZ. So the first application server has an internal web address at internal1.qualys.com, and the other one has a web address called internal2.qualys.com. Now both of these application servers have private IP addresses, and the DNS entries are not registered. So someone trying to access internal1.qualys.com and internal2.qualys.com from the internet is going to get a no such host error, because these application servers are only accessible from within the company network. They are not accessible from the internet. Now, let's say the company decides that they want to enable web access to internal1.qualys.com and internal2.qualys.com. But enabling web access to these servers directly from the internet is a bit dicey. So what the company decides is that it should be integrated with the main web server address, but a reverse proxy scenario would come into picture. So basically now anyone from the internet is able to access internal1.qualys.com and internal2.qualys.com. Now how does that happen? They set up a reverse proxy, and how internally the reverse proxy would work is that anytime a request is made to qualys.com/app1/path1, the reverse proxy rules would kick in and it would be redirected to internal1.qualys.com/path1. So what is happening here is that all requests to app1 are being routed to internal1.qualys.com, and then all requests to app2/path2 are being routed to internal2.qualys.com. So this is how a typical reverse proxy scenario would look like in any company's environment. So let's see how reverse proxying can be set up with Apache. Now Apache is the most popular web server out there, and it's quite easy to set up reverse proxying with Apache. There are a couple of things that can be done. There is a module called mod_proxy, which you can either build when Apache is configured, or if that doesn't happen, you could enable your Apache configuration file, which is http.conf for apache2.conf, and enable the module at runtime. I won't go into specifics of how exactly that could be done, but it's a very simple process. You just need to enable mod proxy when your Apache is being configured. Once Apache has been configured for reverse proxying, there can be two things which are possible. There are directives which you can configure. The first directive is called rewrite rule, and the next directive is called proxy pass match. The reason we are looking at both of these directives is that when we look at the vulnerability, it exploits the way these directives work and the way these directives are written and the rules are written based off these directives. So let's see what these directives do. The first directive is called rewrite rule, and these are both configured in your Apache configuration file. The first thing that is there is the directive name. The second thing that is there here is the regular expression that is to be matched. So if you remember in the first slide, we saw that any request from app1 would be mapped to internal1.qualys.com. So here is the regular expression that you specify, that whenever requests are coming to a particular web server, how you want them to be rerouted to your internal proxy. So you have the regular expression, and then finally you have the rewrite rule. Now you might wonder what the P flag here is for this particular directive. That is just a way of configuring reverse proxying with Apache. So it's just a syntax thing that is there. The other directive that is there is called proxy pass match. It has the same syntax. You have the regular expression, and then you have the rule to where the redirection should happen. So let's see how this works in regards to the first figure that we saw. So I have the rule here. The syntax is right here. Now what would happen is that whenever you have a request to qualys.com/app1 coming in, it's going to try and match the regular expression. So here app1 is going to match this particular regular expression. We have a very generic regular expression here. So I'm just using a simple dot star to see what's happening. So whenever this request comes in, app1 will be matched with this particular regular expression. And then what happens next is that it goes through the reverse proxy, and then whatever is matched here gets extracted in the reverse proxy rule. So if you notice, you have a $1 here. The way regular expression matching and extraction would work is that anything within the first parentheses would be extracted as $1. Most of the companies have a lot complex regular expressions, so there would be multiple levels of parentheses. So if you have, say, multiple parentheses, the first variable to be extracted would be $1, the second one to be extracted would be $2, and so on and so forth. Now what happens here is that we already know that app1 was matched here, so app1 gets assigned to the variable $1, and your final request is internal1.qualys.com/app1. So this is how a rewrite rule would work. Same thing happens with the proxy pass match rule. It's the same thing. Here what is happening is that we have a slightly more complex URL. foo/bar.gif again matches with this particular regular expression, which is everything * followed by .gif and then ending there. So this matches here. So this particular thing is going to be assigned to $1, and our final variable, final URL is going to be internal1.qualys.com/foo/bar.gif, because that is what $1 is assigned to. Alright, so these are all the basics that we needed to understand what will be needed, what a reverse proxy is, how a reverse proxy can be configured with Apache, and what are the different directives. Now let's start with the first thing that I spoke about during the start of the talk. We are going to look at an older reverse proxy issue and try to see what can be done if you were to write a check to detect that particular vulnerability, and what would happen next. So this is the older reverse proxy issue that we are going to be looking at. It has a CV 2011-3368, and if you read through the CV, what it says that the mod proxy module in Apache HTTP server. So I mentioned that to configure reverse proxying for Apache, you need a module called mod_proxy. It says, and then it lists the version of Apache that are affected, and it mentions that if it does not properly interact with the use of rewrite rule and the proxy pass match pattern, then there is a possibility to allow remote attackers to send requests to the intranet servers via a malformed URI. Alright, so what we know so far is that if you have incorrectly configured rewrite rules or proxy pass match directives, then there is a possibility to remotely access your internal systems and internal URL addresses. And it also mentions something about a malformed URI containing an @ character. So we'll see how that works. Now I have a couple of samples here. I have a correct rule and I have an incorrect rule. Now I mentioned earlier that you have a couple of things. You have the proxy pass match rule and you have the rewrite rule. Now both these rules are not required at the same time in your Apache configuration file. You just need one rule. So the vulnerability is in both the rules and it works the same way, but I'm just going to be looking at the rewrite rule. But it's exactly same, the proxy pass match would work the same way. So could you guys tell me what is, I have a correct rule here and an incorrect rule. Can you tell me the difference between the two rules? Yeah, please.
The slash is missing, so it's passing it right to the end of the URI or the URL that's in there.
Exactly. So the only difference between the correct and the incorrect rule is that in the incorrect rule, once the URL ends, there is no / here, right? Now this is a very small difference. It could be just because of an administrator mistake, or the rules that we are looking here are quite simple because it's for an example purpose, but in a real life scenario, your actual regular expressions are very complex. You might have a lot of application servers, like something rerouting to WordPress, something rerouting to some other application. So this expression here is complex, and then the redirect URL is also quite long. So there is a high possibility that someone might just miss this particular /. Alright, now we know that what the difference between a correct and an incorrect rule is. Now the vulnerability states that if your rule is incorrectly configured, an attacker can access systems on the internal network. Let's see how. Now I'd configured a vulnerable target, and on that vulnerable target I had the Apache configuration file to have the incorrect rule. Alright. Now this CVE already had proof of concepts available publicly. So what I did was, just for the sake of creating the signature, creating the check to see how to write a signature, I was just sending those already available proof of concepts to a vulnerable target. So let's see what happens. What I'm doing here is I'm connecting via netcat to this vulnerable Apache Reverse Proxy configuration, and I'm sending it a request get@localhost. Now I'm trying to see how a vulnerable server responds. The response back from the vulnerable server is that it comes back with an HTTP error code of 200 OK, and then you see that the entire content of the website that was running at localhost is being returned. So what happened here is that you send the request get@localhost. Now this particular rewrite rule, because this server is set up as an Apache Reverse Proxy, it's going to try and match the URI to our regular expression. So this particular URI @localhost would match this regular expression, and then as we spoke about, it's going to be assigned to $1, right? So your final request is internal1.qualys.com @localhost. Now can you guys tell me why the web server returned 200 OK and why it gave you the content of the website running at localhost? Yeah.
The @ gets stuck as part of the host name.
Exactly. So the @ sign here was appended here. Now since we had the / missing, our request was internal1.qualys.com @localhost. So in the context of the URL, when you're seeing that, what happens is that you view it as user @localhost. So because of that crafted @ sign, localhost became the main domain, and whatever was preceding localhost became the username of that localhost, right? So that's why it returned a 200 OK response code. There was another, the next thing that, the next proof of concept that I tried was get@qqq.dev.qualys.com. Now this particular web address is any internal website address on your internal network. So this is something that you cannot access from the internet. It is only visible on your internal networks. But when you route the same thing through your Apache Reverse Proxy, the results are that you would get a 200 OK response code, and it would come back with the entire page of whatever web server address you requested. All right. Okay. So now we still have the proof of concept. We know that how a vulnerable target with a incorrect rule responds back. Let's see what happens if we correct the rule back and the target is still vulnerable. We're sending the same request to our vulnerable host, and when you send the request get@localhost, it comes back with a 404 not found response code. And the same thing happens with whenever you request an internal web page. Now the request is still the same, but you don't get the actual page, you don't get through the content of localhost, nor do you get the content of qqq.dev.qualys.com. And the reason is because the rule is correctly configured. So consider the same thing, @localhost gets extracted and it gets assigned value here. So your final request is internal1.qualys.com / @localhost. So obviously the server is not going to be able to find that particular host, and it's going to give a 404 not found response code. So we see here that the difference is very small. Just because the rule was incorrectly configured, someone was able to get through the internal system. All right. Now let's see what happens if you have a patch target and the rule is still incorrect. So the CV that we looked at, Apache released a patch for that, and I set up a patch target and I'm sending the request to the patch target with an incorrect rule. So this is our third scenario. What happens is that when you send the request, the server responds with a 400 bad request error code. Now earlier it was responding with a 200 OK response code, right? So once the patch was applied, Apache was able to figure out that the request was crafted and malformed. So it gave a 400 bad request error code. All right. So what do we know so far? We looked at 3 different scenarios. For the existing reverse proxy issue, we tried the proof of concept on a vulnerable target with an incorrect rule, and we know that it came back with a 200 OK response code. We tried it on a vulnerable target with a correct rule, and we know that it came back with a 404 not found. And then finally we tried it on a non-vulnerable, a patch target, and it came back with a 400 bad request error code. So when I was doing my research, this was good enough for me to create a check, because I knew that how a vulnerable and a patch target would respond back, and then I could write a signature based on that. So that was great. But then what next? Writing the signature to check the issue was the easy part, and it did not take a lot of time. But because I had spent so much time investigating the issue and then creating the targets and figuring out what would happen if things change, I thought that I should pursue this further and do something else with it. So I thought that for someone to check this particular issue, they would have to launch a scan and then figure out. How about if I could just write an open source tool that administrators could run against your Apache configuration file, and then it would tell them that your rewrite rule and your proxy pass match rules are not correctly configured. So I thought that, okay, that's a noble thought. Maybe I could just make the tool open source, and then people could just see if or whether or not their rules are correctly or incorrectly configured. So I started working on that. I spent a couple of days trying to get the best Apache configuration file readers that were out there. And then when I started to write the regular expressions, I figured that real life regular expressions are going to be so complex that there might not be a short way of completely getting the parser rules correct. So those were my limitations, and I thought that, okay, this is not a very good option. Maybe I should look into something else. So a lot of researchers and hackers, they actually look at the patch to see if there are ways to bypass it, or how it was patched, to see if there's anything else that could be done with it. So this idea was attractive, because when I was creating a patch target, I realized that Apache only had like 10 lines of code, and for me it's always I was sort of curious that, okay, within 10 lines of something it was patched and it was correctly configured. So I thought, okay, let me just look at the patch to see what is happening. So that's what I did. So for the reverse proxy issue that we looked at, this is the patch that Apache initially released, and when I configured the patch target, I just had to modify this particular file called protocol.c, and then recompile and reconfigure Apache. So if you look at the patch here, it's just 10 to 12 lines of code, and it's just one if loop that is there, and then it's returning and a bad request error code. So if you look at the patch here, what it's doing is that it is checking for some method underscore number variable, and if it is not set to m underscore connect, and if it is not a parsed URI, and the URI does not begin with a forward slash, and it is not a star or not a null, then it would give a bad request code and return back. So the first thing that came to my mind is that, okay, this seems correct, because what they're trying to do is that they're trying to see if your crafted URI is beginning with a forward slash or not, and if not, it was just bailing out. So I thought that, okay, it feels as if it's doing the correct thing. But to confirm my understanding, I just started reading the comments that preceded the actual patch. So if you look at the comments, it mentions the same thing, some mention of an RFC, and then it says that if the request is not using connect, the parsed URI does not have a scheme, and it does not begin with a forward slash, and it is not star, then fail and give a 400 response code. Now this is the same thing that we thought about when we looked at the patch, right? So you feel that it's doing the right thing. Let's analyze the patch and see. Before we do that, can any of you tell me if there's anything striking in the patch that you feel that you could look at it and think that you could bypass it? Yeah,
It's the not being lumped around the and.
I'm sorry.
It's the not in the last checking there in the if.
This one?
Yeah. You get the not outside of that. So if both of those things are true, then it's not going to be a problem. You're going to get right past that. But I haven't done all that.
Okay, so that could be a possibility. I did not look at that. Anything else?
So the comments say, and the URI is not star, but they're just checking to see if it starts with a star. Am I reading that right? So
The UR.
the comments say it is not star,
Right.
but the actual patch is looking just to see if the first character is star. Those two seem like different things.
That could also be a possibility, but I still did not. So the if loop here has 4 different things, and when I gave this talk at one other conference, actually two other conferences, the first answer that I always got was that if the method is not m underscore connect, and I started thinking that everyone looks at that the first thing, and how did I skip that? But I did not look at the m connect, nor did I look at the URI star or the null character. I looked at something else. Let's see what I looked at. So we know that it was a minimal code change. But the striking point was that the comments mentioned that if the parsed URI did not have a scheme, so I thought that, okay, let me show you what that is. So here it says that if the parsed URI does not have a scheme, and then the same thing is mentioned here. So when I was reading through the comments, I thought that if somehow I could create a URI which had a scheme, then I would bypass the entire if loop, because this particular condition would not be satisfied. So I think the same thing would have worked if it was like, if you could have done something with the star or with the null character or with the m underscore connect method. But I thought that if somehow there was a way to construct a URL which had a scheme, then we would literally bypass a patch, and then you could still modify your proof of concepts, and the server would be vulnerable to the same reverse proxy issue. So, all right. So how to do that? Google to the rescue. Now we know that we need to create a URL with a scheme. Now I had a basic idea, but to understand that what exactly a URL with a scheme was, I made a quick search on Google, and here's what it came up with. this is a URL which has a scheme. The way it works is that the first parameter is the scheme name, which is usually HTTP or FTP or whatever protocol that you're using. The next part is your user information. So you have the username and followed by a colon, and you have the password. That is followed by an @ sign, and then you have the host name. So it's qualys.com. Again, it's followed by a colon. You have a port, and then finally you have the path and your query. For the purposes of our talk, we're going to ignore everything from here. The main focus is going to be the user information, the host name, and the port. Okay, now that we know that this is a URL with a scheme, we somehow need to create a crafted request which has some sort of a scheme so that it would bypass the patch. But what would be our next step? We also need to figure out that how the translation is working. Like if I were to create my own proof of concept or own crafted request, I need to see how Apache is doing all the translations and what is happening. So my step 2 was to review all the Apache Reverse Proxy logs and to study the rewrite translation. Now to set up logging on Apache was quite simple. I just had to do 2 lines of code change in the Apache configuration file. So to set up rewriting, all you need to do is you need to have a directive called rewrite log, and then just assign it a rewrite log, a file name. And then you need to set rewrite log level to 3. Once you do that, you restart Apache. You can monitor all your requests and how the reverse proxy translation is working. So let's see, we're now trying to create a new proof of concept. But before we create our own proof of concept, let's just see what happens if we use the existing proof of concepts that we already had after turning on logging. So I just have the rewrite rule here, and I also have the URL with a scheme. And here's the first request that we looked at, which is get @localhost. Let's see what happens when we try and look at the log file. So it first tries to initiate the rewrite engine, and then this is our requested URI. Right? So it tries to apply the regular expression to the URI. So it mentions that it's trying to apply the pattern star to our URI @localhost. The next thing that happens is that it will try to create the rewritten rule. So our rule will be http:/10.40.2.158 and then @localhost. So we know this from our examples earlier, but the thing to get here from the log file is that every time you try and send in a request, just 5 steps happen and 5 lines of logs are written. It tries to apply a pattern to the URI, and then it comes up with a final request. All right, so that is that. Let's now look at a slightly different example. I have the same rewrite rule here, but the redirect rule has been modified. If you notice, I added a port here after the URL or the IP address. Okay. Now, what is most common HTTP port after port 80? Someone might say 443. What else? 8080, right? So here we are doing a very interesting thing. Our rewrite rule has the rule 10.40.2.158 followed by port 80, and in our request we are trying to request the page 80. Now let's see what happens. This is going to be our URI, which is obviously going to match our regular expression star, and then it's going to be assigned to $1, and the final request that you have is 10.40.2.158:8080, right? So we managed to get access to the page running on port 8080 while we did not have any access. So from an outside network, you were able to create a crafted request and you got access to a page running on a different port, and you did not have access to that earlier. Okay. Now let's try combining the first and the second request and see what is happening. So mind you, we are still at all the previously available proof of concepts that we already had. We are just trying to see how rewriting is working. What happens here is that we are back to our original example. The port has now been removed. When we try to request :@internalserver.qualys.com and followed by the port 8080, it's going to match the URI, and the URI is going to be assigned to $1, and your final request is going to be 10.40.2.158 :@internalserver.qualys.com. Now, can you guys tell me what happens here when you have a particular username followed by :@internalserver.qualys.com in terms of the URI that is here? Exactly, it's a blank password. So what happened here is that 10.40.2.158, which was our username, which was our URL, is now being treated as a username and the colon and then followed by a blank password. So because of this @, it changed the meaning of the entire thing, and you can treat this as a username and then specify whatever internal or web address that you want to specify. Okay, now from step 1, we know what a URL with a scheme is. From step 2, we know how Apache is rewriting rules and how it's translating. For me, step 1, combining step 1 and step 2 was equivalent to creating a new working exploit. So let's see how we can do that. Okay, so I have the URL with a scheme here, and then now we have a patch target, and we're trying to create new proof of concepts, new exploit strings to see that if we can bypass the patch. So I sent out around 20 to 25 different sample requests, but I'm just listing a few here. And if you looked at all the previous 3 examples, we saw that from the logs there were 5 lines of code and 5 different patterns being matched up. So here what is happening is that I'm sending the request get @localhost followed by 2 colons and then 8080. I'm sent here the next request, I have 2 @. So what my basic purpose was trying to leverage the URL delimiters, which were colon and @, because I knew that everything following the first colon was the password and everything following the second colon was the port, and then there was an @ delimiter. So I tried creating requests which had multiple delimiters, like multiple @ and multiple colons, and then logging what the URIs were being extracted. Now there's a pattern here in terms of the URI being extracted. Can you spot the pattern from the request and the URI? I'm sorry? Exactly. So everything following the first occurrence of the colon is being treated as the URI, right? So here everything following the first colon is colon 8080. Here everything following the first colon. So I noticed that having 2 @ did not help a lot, but having 2 colons did, because as soon as you had 2 colons to the request URI, everything that followed the first occurrence of the colon would be treated as part of the URI. So you could leverage this particular part to either use it as a password or as a port. So all right, we're inching closer towards the POC. Here we have the exact two columns from our previous slide. I just have the translated request here, and we already have two proof of concepts right here based off the, the premises that everything following the first colon was a URI. Can you spot the proof of concepts? Okay. So this is the very first one. Our request of @localhost colon 8080 resulted in the URI of HTTP 10.40.2.158 with 8080. Now remember, from the outside world, all you're doing is you're trying to access @localhost 8080. But because it went through the entire reverse proxy translation, what happened was that the translated request let you access port 8080 on this particular page, right? And the next proof of concept is right here, wherein you're trying to add a random string followed by a colon @internal1.qualys.com. So your final request is 10.40.2.158 @internal1.qualys.com. So what happened is that this particular thing was converted to a username, and then you were able to access internal1.qualys.com. Right, so we just created two proof of concepts that worked on patch targets, and now it's time to exploit it. So all I'm doing here is that I'm sending my first proof of concept, get @localhost colon 8080, and seeing what is happening. So if you look at the response here, it comes back with a 200 OK response code, and you see whatever internal page is there on port 8080. So basically, by just understanding what a URL with a scheme is and then trying to leverage that and creating crafted requests, we are able to create new proof of concepts that worked on a patch target. For my next request, I'm sending the request a random string followed by a colon @QQQ.qualys.com, and the result is the same. It comes back with a 200 OK response code, and you're able to access the internal system. Okay, so after I discovered the POC, we do have a responsible disclosure policy at Qualys. So we reported the issue to Apache, and Apache was very quick in responding back. They assigned it a CVE, and then there was quite a bit of back and forth between the guy I was interacting with, and they mentioned that they wanted to make the issue public because the initial part of the code, they were not sure of how they wanted to patch it. So it was made public, and a couple of months later, Apache patched it with Apache 2.2.22. Let's see how it was patched, because I was curious to know that. So the first part of the code that was there, it was yanked out. The file that we looked at in protocol.c, because I was trying to make changes to a common file, and what they ended up doing was they ended up patching the proxy.c module and the rewrite module, and they're doing the same thing. They're trying to see if the URI begins with a / or not, and if not, they just bail out by giving a bad request error code. Now, if you think from a broader perspective, finding the vulnerability was not very difficult. We just did a couple of things. The only tools that we used were Netcat and some basic Googling skills, right? So things like these happen, like patches come out, and sometimes there are loopholes in the patches that if you just look at the patch, there is a way to just bypass it and go past it. I also have a tool which is available to see if you have a reverse proxy configuration and if you want to check if your rules are correctly or incorrectly configured. It's a standalone Perl script. You could download it from this particular URL, and all you need to do is provide it with your vulnerable Apache IP, and then if you have or if you know of internal web server addresses, I also have an option. you could try providing that, and it might come back with a 200 OK response code if the rules are not correctly configured. And here are a few references I used to put up this presentation. And finally, if you guys have questions. Questions? Right. Thank you very much.